Okay, Elena, I want to write with my pen sometime. If you let me,
Yeah,
I
sure, of
will.
course. Yeah, okay.
Okay.
Okay, good, very nice. Okay, I'm
Okay.
really happy. I'm really happy to introduce uh,
Okay.
our friend Saeid Alikhani from Yas University, Iran. And it will be the talk, well, actually it is invited talk. I asked Saeid to give us a survey on some new and old results on domination theory in graph theory. So that is something like an invited talk in the framework of this workshop. So the floor is yours.
Okay. Thank you very much, Elena. Uh, I would say hello to everybody, and here is the afternoon, and I hope to have a good time. Thank you, Elena, to invite me into this workshop. Actually, I want to say something about the coloring of graph, which is uh, called distribution coloring. This work is joined with my postdoc researcher, Dr. Mohammad Hadi Shekari at the University of Iran. Okay, what is the distinguishing coloring or distinguishing labeling? The distinguishing number denoted by capital D of G is the least number D such that G admits a vertex coloring with G colors.
Saeed, I'm sorry, we still can
okay.
see only the first slide.
Sorry?
Well, still we can see only the first slide with the title. Is it okay?
Oh, no, it's not okay. No, you see my slide or not?
We see the first slide.
Oh, maybe I check another slide. I have the PDF and no.
Yeah, now it works. Yeah, so good,
Okay.
good. Okay.
Okay, sorry. We have many problems in internet in Iran. Sorry for this. Okay, the distinguishing number denoted by capital D of G and is the least number D such that G admits a vertex coloring with the colors that is only preserved by trivial automorphism. This index introduced by Albertson and Collins in 1986. And actually, for version of two colors, and this is studied by Wabai, who is in US, and I think he studied for in two colors this in 1974, I think. Anyway, after 19 years later, the distinguishing index or the age version of this coloring denoted by D prime of G, and this is a least number D such that G has an age labeling with the labels that is present only by identity automorphism. And this index introduced by Monika Prisniak and Rafael Kalinowski in Poland. Okay, I want to show by very simple example here. For example, if we have a pass, for example, of order n, I want to color the vertex of this pass such that preserve only by identity automorphism of paths. Okay, you know that every automorphism of this graph map the end vertex of this path to end vertex. So by definition, we must color these two vertex differently. So I use the color one for the first leaf, and I use the color two for the another leaf, and I can, since in the this coloring, in distinguishing coloring, the coloring is not proper. Of course, it can be proper, but in this presentation, I consider just not proper. So I can use another just color one to use the least number of colors. Okay, so by this coloring, I show that the distinguishing number of paths is equal to 2 for every n greater than or equal, for example, 3 or 4. And also we have this coloring for age coloring of this paths. Note that again, by the definition of distinguishing coloring, I would like to this coloring preserved only by identity automorphism. So this pendant age should have, for example, the color 1, but this one can be color 2, different with this one, and another edges can be colored with 1 or 2. Okay, so again, we have the distinguishing index or age distinguishing number of paths of length n minus 1, or order n is equal to 2. Okay, so this is a definition of the distinguishing number and distinguishing index. And most of the paper, I think more than 120 papers have published in the coloring, in this coloring, distinguishing coloring of the graphs. And most of them first compute the distinguishing number and index for a specific graphs. And note that the computing of the complexity of computation of this two index is NP compute. And so, for example, you see here me and my former PhD student Saeid Sultani in 2017 proved that the distinguishing number of friendship graph, which is a join of K1 and NK2 obtained by this sealing formula. And also for age version, you see a number again is sealing formula, which is harder than in a vertex version. Okay, and not that, let me to say something about this graph. You know, we have a K1 join. Let me to denote the join of the graph with V. So I have just one K1 and K2. This is one K2 and this one another K2 and so on. So this is a friendship graph that I think all of you know about this graph. Okay. If I would like to color this friendship graph with distinguishing coloring, this vertex should be have the fixed color because have degree I think 2n, and so must be mapped in itself. And but since I would like to the coloring preserve only by identity automorphism, so I color, for example, the base of this triangle with 1 and 2, and I cannot I cannot color this base of this triangle again by 1 and 2. So I use another color, for example, 3, 2 and 3, and here I should use 3 and 1 and 1 and 4 and so on. And by this kind of coloring, I can obtain this formula for distinguishing index of the friendship graph. And you can see the details of this proof of this theorem in the paper which published in the Philomath in 2017, if you are interested. And there are many results in this in these parameters. For example, what happened to distinguishing in the number and distinguishing index when we remove vertex, or for example, we remove edge from a graph. You see here in the first theorem in this slide that if we remove a vertex from a graph, then the distribution number of G minus V decreases by 1 and increase by 2 times of the distribution number of G. And again, we have the similar result for edge distribution number of graph. And in the second theorem in this slide, you see that if we remove an edge from a graph, then distribution number of G minus E decreases by 2 and increase also by 2. And there are many another operation on graph that we can study its distribution number and index. For example, you see here the contraction of a vertex. Note that the contraction of a vertex V in the graph G denoted by usually by G circ V or G of V, or maybe G/V, which is obtained by, from the graph G, and we remove all edges between any pair of neighbors of V. And here, note that the vertex V is not removed from the graph. If we do this operation on a graph, then distribution number of G OV greater than or equal to the distribution of graph minus 1, and also edge distribution index is less than or equal to distribution index, edge distribution index at G of plus 1. Okay, now we ask a question. Actually, I learned about this coloring in the Poland when I participated in the actually CID conference in the Poland, coloring independence and domination. Very good, I think, conference in the Europe. And after that, I was external examiner of one of the PhD students who is my co-author in this presentation, Hadi Shekari's, in Mashhad University in Iran. I asked a question from Muhammad Hadi that in this coloring, how many coloring we can have with, for example, with fixed color. Let me to explain more here. Note that in the elementary graph theory and in the coloring of graph, when we study the chromatic root, for example, chromatic number and proper coloring. For example, we have, suppose that we have a lambda color, and we can ask how many ways that we can color the graph G with lambda color. The answer of this question is a polynomial in lambda, that which is usually denoted by PGM lambda, okay? And this polynomial called the chromatic polynomial graph. So I asked this question, I think in the first, for the first time, that is it true that we have this similar, for example, polynomial for distribution coloring or not? But then after that, we checked that this is not very easy to answer to this question, but I would like to say something about this subject here. First, I did this definition that says if two coloring C1 and C2 are called equivalent if there is automorphism alpha of G such that the C1 of B equal to C2 of alpha for every vertex V. Ahmadi, Ali, Nazipur, and Shekari's actually define this definition, which is that the number of non-equivalent distribution coloring with exactly K color with exactly k color denoted by capital phi sub k, and with k color denoted by phi sub k. Okay, so note that the number of distinguishing coloring with exactly k colors, which denoted by capital phi sub k, and with k colors means that you can use 1, 2, or 3 k colors denoted by phi sub k. Okay, obviously these two parameters, capital phi and small phi, are equal for k equal to distinguishing number of g. In other words, the capital phi sub d of g equal to phi sub d of g. And by the definition of the capital phi, we have this equality that says that phi sub k of g is equal to summation of phi sub I from distinguishing number of g to the k. And very easy to see that the phi sub k of complete graph of order n is just is non-zero only for k equal to n, and this number is 1. And again, Ahmadi, and Shekari is obtained very nice, I think, recursive formula for the number of exactly k coloring, distinguishing k coloring of paths of order. And that you see here a recursive formula, which is a k choose 2, k to the n minus 2 plus k times capital phi sub k of Pn minus 2. And actually, I think there it's not bad to say something about the SketchUp proof. Not that I would like to prove that the phi sub k of the graph Pn is equal to k choose 2, k to the n minus 2 plus k times capital phi sub k of Pn minus 2. Okay, I would like to prove this. It is easy for the proof is easy for n equal to 2 or 2, and for n greater than or equal 4. We know that for a path, as I said before, we know that the two n vertices of Pn either have different colors. We have two cases. These two n vertices have different colors, or maybe the same color. Okay, if have a different color, for example, 1 and 2, color 1 and 2, then obviously I can choose these two colors from k color by k choose 2 ways, and after these, the internal vertices can have any possible k to the n minus 1, k to the n minus 2 combination. Okay, I can color this, for example, the second vertex by k color, this one again by k color, and so on. So for the case 1, we have k choose 2 times to the k to the n minus 2 ways to color this graph by distinguishing color. And if for the case 2 that says that if the n vertices reach the same color, for example, I use here just color 1 for the n vertex, then obviously I can choose this color with k choose 1 ways, and then obviously I should color this Pn minus 2, internal Pn minus 2 with distinguishing coloring that by the definition coloring of this Pn minus 2 is equal to capital phi use k color of Pn minus 2. So by the addition principle, obviously we have this result. So the result is not so hard. So I think this result is the first result in the counting the number of distribution coloring of the graph. And if we want to know about the small phi sub k of Pn, which is the number of k coloring, the distribution k coloring of paths, when k can be greater than or equal d of g, we have this recursive formula, but you see here this recursive formula is not homogeneous, and we have some terms which is dependent to Stirling the second Stirling number that you know about the Stirling second of the second kind, which is denoted by capital S and a K, and this is a ways of partition of a set of n object into k non-empty subset. So you see here we need this Stirling number to obtain this number of distribution coloring of the paths. And again, the proof is not so hard, and it's very similar to this method of the counting the proof, counting the coloring in the previous theorem. And again, we can count the number of coloring, distinguishing coloring for many another graphs, but not that are not easy at all. For example, if you consider the complete bipartite graph with the same size in the part, for example, x and y, then the number of exactly k coloring of this bipartite graph obtained by this formula. Note that the distribution number of this graph, bipartite graph, is n plus 1, and the proof is easy because note that we should color the vertices of each part different from other vertices within the part, and the two parts of this graph have to be colored differently. Okay, since we have chosen n color out of k color to color the vertices of a part k and n, we cannot color other parts by the same palette of colors. Okay, anyway, you can refer to the paper in discrete mathematics by these authors in 2020 for details of the proof. Okay. Again, okay, we have this note here that says if G is a graph of order n, and we suppose that we want to color distinguishing the vertices of G with exactly n colors, then every vertex obviously must receive a color different from the others, which gives rise to n factorial coloring. However, in order to count non-equivalent coloring, we should consider the coloring of modulus of the automorphism group of G. So we have this nice observation for the number of n coloring. N is the order of the graph G. We have n coloring of the graph G obtained by n factorial over the number of automorphism of the graph G. Okay. By the previous observation, we can ask whether there are numbers k less than or equal n such that any k coloring of a graph of order n is distinguishing or not. Okay. Ahmed Alikhani for Chicago is define this another parameter denoted by theta of g, the distinguishing, and call this this parameter by distinguishing threshold. The distinguishing threshold of a graph denoted by theta of g and is the least number of color k such that every k coloring is distinguishing. Okay, so what is the theta g? Theta g is the least number of color k such that every k coloring is distinguishing. Now we want to obtain and compute the theta of g for specific graph. For example, you see here for complete graph kn and empty graph kn overline, which is obviously equal to n. And for example, for complete bipartite graph, you see theta, which is a threshold distinguishing threshold of complete bipartite graph is n plus n. And it's not so hard to see this, the distinguishing threshold for pass is equal to ceiling number of n half plus 1, and per cycle is floor of n over 2 plus 2. And let me say something about why the part 1 is true. Note that the automorphism, look at the automorphism group of paths, Pn, induce the ceiling in our two orbits on its vertices y. Each orbit contain at most two vertices by the pigeonhole principle. Any combination of ceiling in our 2 plus 1 colors on n vertices of Pn breaks at this one orbit. In another way, since with the ceiling and our 2 colors, there is no distinguishing coloring, so theta of Pn is exactly this number that you see here. Okay. So for any coloring for any number k which is greater than or equal to this theta, the coloring of the path with k color is distinguishing. Okay. And you see here a result about the distinguishing threshold of Kneser graph, a specific Kneser graph. You see, you know that the Kneser graph denoted by capital K and K and is a graph whose vertex set is the set of all K subsets of 1, 2, and n, and 2 vertices are adjacent if their corresponding set do not intersect. And you see here a result about distinguishing threshold of K and K of n and 2. And in particular, if we substitute n by 10, then we have the distinguishing threshold for Peterson graph equal to A. And this theorem shows the importance of the distinguishing threshold in counting the number of non-equivalent distinguishing coloring. For large enough K, we have this equality that says the twice of K of G is equal to K factorial times the second Stirling number over the order of automorphism group of G. Okay, so you see that for every k greater than or equal theta of g, we have by this formula we have the number of non-equivalent solutions. Since the number of automorphism group of Pn is 2, so we have this corollary that phi sub k of Pn equal to k factorial second assembly number over 2, and also since the number of automorphism group of cycles is n, we have this equality for the number of coloring of cycles Cn. Okay, you don't get presented by a product as cyclic permutation for an automorphism alpha and a vertex V, the order tuple sigma, which is V alpha of V alpha to the 2 of V, and so on, to the alpha to the R minus 1 of V is a cycle of length R, and R, you know, is the least number that alpha to the R of V is V. The number of cycles of an automorphism of alpha is shown by the modulus of alpha, and so we have this result that the distribution threshold over any graph is the maximum of number of cycles of automorphism of graph, which is not identity plus 1. And by this lemma, we have this simple corollary that theta of G is 2 if and only the order of graph is 2. And you see a result about actually necessary condition for a graph to have a distribution in threshold equal to 3. If G is a graph of order n have theta of G is equal to 3, then either the order of graph is 3, or in this case, that says the order is 2 times of P, where P is a prime number, which is not T and 5, and also G is connected by regular graph with degree partition A1 and A2, and note that in this subgraph of A1 and A2 are non-isomorphic circular graphs. So this theorem says about graphs whose have distribution and threshold are equal to 3. And you see here about distinguishing threshold of Cartesian product of graphs. For example, let me to say if G equal to K is a prime factorization to mutually non-isomorphic connected graphs, then theta of G is equal to maximum of theta of Gi minus 1 times the number of vertices of G over the order of Gi plus 1. Okay, this is so with this formula we can obtain the distribution in threshold of Cartesian product of graphs. And again, if we substitute in the previous theorem any G1, G2, and Gk by G, then we will have this corollary that the theta of G to the K, where Gk is the K's Cartesian power of G, is equal to this number. And recently, we defined the age distribution threshold of G, and we denoted this parameter by theta prime of G. And obviously, this is least number K such that any edge coloring of graph with k colors is distribution. And if symmetries of G can be broken by edge coloring, then this edge distinguishing threshold of G obviously is less than or equal to the number of G, size of G. And similar to vertex version of threshold of a graph, distinguishing threshold of a graph, we have this theorem about theta prime of some specific graph, such as P of n, P sub n, C of n, and so on, that are not so difficult to prove these parameters. Okay, and again, we can have similar result for theta prime base of cardinality of number of cycles of automorphism. And this lemma says that if G is a graph whose symmetries can be broken by H coloring, then theta prime of G is the maximum of modulus of alpha sub E, where alpha is non-identity automorphism plus 1, and this notation, the modulus alpha sub E is the number of H cycle of alpha. And by this lemma, we have this theorem or corollary that says if theta prime of a graph be 2, then G is a K1 and 2 or P3. So, and just we have one graph whose half theta prime is equal to 2. And to characterize, to say something about to graph whose half theta prime is equal to 3, I need some notation here. For example, we use this notation bracket V and set A for the set of H whose one of the endpoints is on the vertex V, and another belongs to the set A. And this theorem says if G is the graph with theta equal to 3, and note that I said before that if theta is 3, then the order of graph is 3, or the number of vertices is 2p. P is a prime number, which is not 3 and 5. So here, the assumption of the theorem is suppose that the order is greater than 3. So we should write if G is a graph with theta is 3 and the number of vertices 2p. Then for every v in the AI, in the set AI, we should have the cardinality of bracket v and AI plus 1 between 3 and p minus 3. And so we have this theorem that if G is a connected graph with theta prime of G is 3, then G is P4, K1 and 3, and Kj. Okay, so this is a necessary condition for a graph whose have H distribution threshold equal to 3. And here we have another result for theta. It's not for theta free. If G is a graph with order greater than 3, then and theta is 3, then we can say something about the line graph, and here G cannot be a line graph. Okay, in the rest of my talk, I would like to say something about the distribution threshold of some graph operations. Actually, this result that I would say about them is with my four co-author Mamadhadi Shekaviz, Talepur, Bahman Ahmadi and Shidar. And this paper will be published in Springer Journal, I think. I don't remember the name, but you can reach the paper in the archive now. Since the number of quasar here is 5, I cannot write all of them, and I use just some STAs, STASA for the first family name of my quasar. Okay, let me to define operation between a graph. We have some graph, disjoint graph G1, G2, and GK, and I choose from any graph, I choose a vertex. For example, from the graph G1, I choose U1, from G2, I choose U2, and so on. The vertex sum of this K graph is this graph, denoted by this notation that you see some U in the below of plus, and obtained from G1, G2, and GK by identifying the vertices UI as the same vertex U. We call this vertex U as a central vertex of the vertex sum, and the vertex sum of T copies of a graph G at a vertex U is denoted by G sub U to the T. And for the sake of simplicity, we may assume that the vertex U belongs to all of the G sub I. And let me to recall something about the stabilizer. Recall that when a group gamma, capital gamma X on set X, and X the element in the capital X, the stabilizer of X in gamma denotes is a subgroup of gamma consisting the element G such that G of X is equal to X. All of you know, I think about this definition. And if G is a graph and consider the natural action of automorphism on the vertices of G and fix a vertex U, it is easy to see that the function which maps any alpha in the stabilizer of U in automorphism of G2 is restriction on G minus 2 if we have group injection. And we have this well-known fact that, which is I write here as a lemma, if G is a graph and U be a vertex, then a stabilizer of U in automorphism group of G is isomorphic to that group of the automorphism of G minus 2. And actually this motivates us to consider the vertices U for which these two groups are isomorphic. And we have this definition that if G is a graph and U be a vertex in G, then we say U is a STD vertex if the stabilizer of this vertex in automorphism group of G is isomorphic to automorphism of G minus U. And we have this theorem about the STD vertex, and we have a graph G which is connected, and we choose a vertex U, and we say this U is the STD, then every distribution coloring of graph induces a distribution coloring on G minus U. But the converse is not necessarily true. And here, if these G1, G2, and GT be connected or connected graph, a vertex and U is STD in each GI if and only if U is STD with vertex and vertex sum. And you see your, I think, very nice theorem about distinguishing number of G sub u to the T, distribution number of the sum of some graph, vertex sum, which is, as I said before, is an operation between some graph. Distribution number of G sub u to the T is less than or equal minimum of K, such that Y sub K of G minus U is greater than or equal T. So this theorem shows that a study of the number of exactly K coloring of some subgroups of a graph can be useful for finding the distribution number of some product of graph, for example, V sum. And here the equality holds if uses vertex of graph. As an immediate consequence of the previous theorem, one observed the following corollary, that it is says that it is a vertex sum of T copies of complete graph Kn at any vertex, then distribution number of this graph is the minimum K such that K choose n minus 1 greater than or equal T. And in particular for case and 3, N3, 4, and 5, you see the same number that give us the exactly number of distribution number of this graph. And as another result and corollary, you see here the distribution number of G. G here is vertex sum of T cycles of length N, and this distribution number is equal to minimum K, such that K to the N minus 1 minus K to the sin N minus 1 over 2 is greater than or equal to T. And in particular for case when N is out, we have this same formula for distribution number. And maybe we can turn out, we can turn our attention to the vertex sums of non-isomorphic graphs. And that here we consider two connected graphs. And we have this theorem that if G1, G2, and GT are two connected mutually non-isomorphic graphs, all having U as a STB vertex, and G be their vertex sum at U, then distribution number of G is the maximum of distribution of GI minus U. And note that in this theorem, the necessity of the assumption of this theorem is important. For example, in this figure, bus graphs here, G1 and G2 are two connected. The vertex U is not STB in G2, and distribution G1 minus U is 2, and distribution also of G2 minus U is 3, but the distribution of vertex sum of these two graphs is 2. And also you can see here a vertex sum of two graphs which are not too connected with the U is STB in both of them. So the assumption in this theorem are necessary. And let me to say about this theorem that if G is a graph, if G is a vertex sum at U of two connected graph G1, G2, and G3, which all have U as a STB vertex, and if G prime is the disjunct union of GI minus U, then the distribution threshold of G is equal to distribution threshold of G prime plus 1. And as a immediate result, we have this theorem that if G is the vertex sum of T cycles of length and then distribution threshold of this graph obtained by this synonym minus 1 over 2 plus and minus 1 times T minus 1 plus 2. And I think this is the last slide of my presentation about the distribution number of corner of two graphs. You know, I think all of you know about the corner product. Let me to recall this operation in the graph theory. Let me draw the graph G as like this and draw the graph H as like a square, for example. Then the corner product, which denoted by G circ H, obtained by one copy of G and the number of vertices copy of H in the above of any vertex of G. For example, I put the graph H here and then connect this vertex to all of vertices in the edge and do also this operation for another copy of H here and so on. Okay, so this kind of operation is the kernel to graph, and we studied actually the distribution number and distribution index of kernel of the graph in about 5 years ago with my student Samane. But here is another approach that uses the number of non-equivalent distribution coloring of edge. You see this nice formula that gives us the distribution number of kernel of G and H is the minimum case such that the phi sub k of H is greater than or equal to G of G over K. And here is the last theorem that is about the distribution threshold of kernel of two graphs. That you see here is automorphism of a graph X is not identity, then we can obtain the distribution threshold of GOH by this formula. And if the automorphism of H is identity, then we have these formula. Okay, thank you very much for your attention. I hope that this presentation has been useful for you and your student and all of the colleagues here. I'm so sorry for problem in internet and webcam. I don't know why, but I think there is a problem for all of them in my country because we do not have good situation for internet in Iran. No, thank you very much, Elena. And
okay, thank you very much. Actually, everything was fine and your presentation is perfect. Thank you.
Okay,
Are there any questions to Saeid?
Maybe Hamid have a question. I see the name of Hamid. I hope the Hamid is okay.
Okay, everything is fine. Well, actually,
Okay.
well, I have a simple question. So you consider a lot of products,
Yes.
right here. So are there any other interesting operations you are working with?
Yes, as you say, there are many products. Actually, someone who was in my former PhD student studied the distribution number and distribution index for I think about 7 graph products, and just the title of her thesis was about distribution number, but we can do the similar thing about this distinguishing threshold that introduced recently, but we did just for one or two graph product, and for another graph products, these are open problems, and we can, for example, do for Cartesian for a strong product, for example, neighborhood corona. There are many, yes, open problems in this.
Okay.
Yes.
Okay, which means that in future we can hear some new result, right?
Okay.
Okay. Okay. Thank you. Thank you very much. Thank you.
Okay.
Yeah.
Thank you so much.